Hello everyone, welcome to the class. Today we will discuss about the phase and the magnitude response of the transfer functions. Uh, and to explain that further, uh, let's take one example. And the example says the system is uh, 1 by 2 at n equal to 0. The value of the sample is 1 at n equal to 1. It is 1 by 2 at n equal to 2, and the rest of the values are all zeros. And to get the transfer function out of this and further the magnitude and the phase response, we will have to take the Z transform to start with. So once you take the Z transform corresponding to H0, this is the value, corresponding to H1, this is the value, corresponding to H2, this is the value. The final expression after the Z transform is 1 by 2 plus Z to the power minus 1 plus 1 by 2 Z to the power minus 2. This is the transfer function. This is Hz. Now, if you have to take if you have to get the frequency response of this system, we know that Z has to be replaced with e to the power j small omega, where small omega is the digital frequency. Now you replace Z with e to the power j omega. Actually, at this point, it is e to the power j omega only. But for simplicity, we put it simple omega. But inside the expression, we will replace Z with e to the power j omega because that will involve the actual calculations. To separate out the magnitude and the phase part of the frequency response, because we know that frequency response of a system has two parts. One is the magnitude part, the other is the phase part. So to get that, we take out the c to the power minus j omega and put everything inside the bracket and accordingly manipulate the expression inside the bracket. We know that by applying the Euler's formula, where e to the power j omega plus e to the power minus j omega is actually uh, 2 cos omega, or e to the power j omega plus e to the power minus j omega by 2 is cos omega. So that's how we get this term e to the power minus j omega, which is already outside the bracket, 1 plus cos omega. Now e to the power minus j omega is actually this phasor represents the phase value, and 1 plus cos omega represents the magnitude value. Therefore, our phase value is minus omega if you take out from the phase value from here, from this part. Now we know that the magnitude part can be positive also and can be negative also. In case the magnitude part is negative, right? In that case, that will depend upon how omega varies. Now, for the omega values for which the magnitude part is positive, the phase remains the same. But for the values of omega for which this magnitude part is negative, in that case, the phase will have to adjust this negative value also. That means the phase will accommodate this negative value by having a jump of plus minus pi. Now, how you make the plus minus pi jump will depend upon that you have to keep the phase response always an odd function. Magnitude response is always an even function, and phase response is always an odd function. Please remember that point. But in our example, it is 1 plus cos omega. This is never going to be negative. Therefore, the amplitude function is never negative here. Therefore, there is no phase jumps of plus minus pi. So the final value of the phase will be minus omega only. So this is the plot of the magnitude response from 1 plus cos omega. So this is the magnitude value. Only the positive above the omega axis will be the values will be there because we are taking the modulus. Magnitude responses are plotted like this only. This is the phase response. the slope of the phase, it is minus omega, slope is negative, therefore we get a straight line like this. Okay, so let's take one more example where the example is of a delta function where the value of the function is 1 only at n equal to 0. Rest all values are 0 at all the points of at all n points. Now if you try to get the frequency response of the system, frequency response will be a flat value of 1 from minus pi to pi, and the phase will be 0 from minus pi to pi. Okay, we all know that the characteristics of the delta function. Now let's take the case 2 where the delta function is shifted by k. So that means this graph shows the delta value where the impulse function is shifted by k, and only at n equal to k the value is 1. For all the rest of the samples the value is 0. To plot the magnitude and phase response of this system, we first take the Z transform. So it is 1 basically into Z to the power minus k. 1 is the magnitude part. So if you want to get the frequency response, what you do is you replace Z with e to the power j omega. I have already explained this part. This will be h omega only. And you replace Z with e to the power j omega, you get this value. Now, what is the magnitude? What is the magnitude part? It is 1. It is always positive. So this is how the magnitude part is plotted. This b omega tells me this is the magnitude part. Now let's look at the phase part. This is very important actually. This will explain the third case where you have to adjust the phase. Phase part is having a negative slope going from this point to this point. It is a straight line, right? Now the point is that the phase value will never exceed either pi or minus pi. Whenever the phase value is trying to exceed pi, it will make a jump of 2 pi. That means it will wrap around, and from pi it will come to minus pi. So that means it makes a wraparound of 2 pi phase. When phase exceeds plus minus pi range, when phase exceeds plus minus pi range, a jump of plus minus 2 pi is needed to bring the phase back into plus minus pi range, because to bring it back into the plus minus pi range, so this value comes here, again the phase starts along this side. So three things we need to learn about the phase response. The first is the whatever the phase response we get from the frequency response part, that's one, that will be the actual value. Second is depending on the magnitude part, whether for the values of small omega, for for what values of small omega the magnitude is positive, in that case the phase remains same. But those values of omega for which the magnitude becomes negative, you will have to make adjustments of plus minus pi. And the third thing is that the phase value will never exceed plus minus pi range. So therefore a jump of plus minus 2 pi is needed to bring the phase back into this plus minus pi range. So while plotting phase responses, we need to keep always these things in mind. From the previous examples, we note that there are two occasions for which the phase function experiences discontinuities or jumps. Actually, this is a discontinuity and we wrap around by plus 2 pi. This is also, let me, it's not, whenever you make a plus minus pi jump also, that will again be a discontinuity. So a jump of plus minus 2 pi occurs to maintain the phase function within the principal value range of minus pi to pi. That's the range of the digital frequency. A jump of plus minus pi occurs when v omega undergoes a change of sign. The sign of the phase jump is chosen such that, this is important again, I have already explained this, is chosen such that the resulting phase function is odd, and after the jump lies in the minus pi to pi range, closed interval. Okay, so this was all about the magnitude. No, one more example is there. So let's look at this example. Determine and sketch the magnitude and phase response of the first order recursive filter. Now this is an IIR filter. Why this is an IIR filter? Because you have a feedback path also. This is the output. This is the difference equation giving us the output in terms of yn is related with input plus the previous samples, previous output samples. And what is A? A is a scaling factor. We have to find out the magnitude and phase response of the first order recursive. Why this is first order? Because if you take the Z transform, you will come to know that the highest power of Z is 1 only in the expression. So therefore, it is a first order recursive filter. Now, how to get the transfer function out of this? You take the Z transform. This will be YZ, XZ. And this will again be will give you YZ. So you get YZ by XZ, which is basically XZ. We know that, and the expression comes out to be 1 over 1 minus A Z to the power minus 1. We already know that when you have to draw the frequency response, you have to replace Z with e to the power j omega. So we get this frequency response. We need to plot the magnitude and phase responses. So therefore, to separate out we need to separate out the magnitude and phase part clearly, so that we can draw those, we can get the value, and we can analyze those expressions of magnitude and phase response. So to do that, you multiply and divide by 1 minus a e to the power j omega on the numerator and the denominator. So in that case, you will be able to separate out, this is the real part of the frequency response. This will become the imaginary part once you multiply inside. All right, then what is the phase part? Phase tangent phi you can get by dividing the imaginary part with the real part. So this is my imaginary part, this is real part, and we get tangent phi will give me the phase value. So if you take tan to the other side, you get tan inverse. So once you get tan inverse, you will get the phase value as minus a sine omega over 1 minus cos omega. And let's now try to plot the this, because this is the magnitude part, so we can plot this magnitude part here. I have given the value here, 1 over 1 minus 2a cos omega plus a square. All right, and you can further simplify, and you get this phase, you get this magnitude response. And further, assuming 0 is less than a is less than 1, you can also simplify the expression by another method, which is h omega into h complex conjugate of h omega. You can get h omega square. So once you get 1 over 1 minus, so you take the conjugate here and you further simplify this, you will get this expression of magnitude response. You plot, you vary the values of omega, keeping a between 0 and 1, you will get this type of curve within minus pi to pi range. And you notice here that this is an even symmetry, right? And the phase part, phase is basically your tan inverse of this value. So phase will be an odd symmetry, very clear from the graph, and it is a non-linear phase. It is not linear phase here in this case, because it is represented by tan inverse. Okay, so This is how you will be able to find out the magnitude and phase responses of the systems. Okay. Now let's let's go a little deep into the behavior of the transfer functions. We know that the zeros are the numerator, zeros lie in the numerator and basically explain those values for which the transfer function goes to 0, and poles represent the values on the denominator side, and a pole represents the poles represent those values for which the transfer function goes to infinity. So that's what is said here. A pole is a root of the denominator of the transfer function. Conversely, a 0 is a root of the numerator of the transfer function. Here the transfer function will go to infinity. Here the transfer function will go to 0. So those values are basically for which the transfer function goes to either 0 or infinity. Those values represent zeros and poles respectively. Now this point is also important because you make a transfer function with the help of poles and zeros. Now each pole gives a minus 6 dB per octave or minus 20 dB per decade response, whereas each zero gives a plus 6 dB. This is important. Zero gives a plus 6 dB per octave or plus 20 dB per decade response, whereas a pole gives the reverse of that, which is minus 6 dB per octave or minus 20 dB per decade. Now, a pole corresponds to a corner frequency at which the slope of the magnitude curve decreases by 20 dB per decade. That means you must understand this. Once you introduce a pole in the transfer function, what will happen? You will be able to roll the response of the filter or the system sharp by introducing more poles. Once you introduce a zero, there will be lifting of the response upside. Pole will dip it down downside by 20 dB per decade. Now, what is the meaning of 6 dB per octave? Once you double the frequency, it will be the curve will bend down by 6 dBs. And 20 dB per decade, once you take the 10, it is for the 10 times of the present frequency. Once you look at that value, it will be dipping by 20 dB. Or in the case of a zero, it will be lifting by 6 dB per octave. For the doubling of the frequency, 6 dB will be lifted. For the 10 times of the frequency, it will be lifted up by plus 20 dB. So that's how you will be able to understand the magnitude response and further the phase response by introducing zero or a pole in the system. All right. So if, because the pole and zero will actually determine the roll off of the filters or the whether the filter the the low pass filter or the high pass filter, the band pass filter, band stop, those will be actually determined by the coefficients of the filter. All right. Now let's look at one very important um, concept of minimum phase, maximum phase, and mixed phase systems. Because we know that the system will remain stable if the poles lie inside the unit circle. So mod z equal to 1, this basically defines the limits of the unit circle. So if the poles lie inside the unit circle, then only the system will be a stable system. Otherwise, the system will be unstable. Zeros can lie anywhere in the phase in the pole zero plot. This is the pole zero plot. Now this side is the real part and this side is the imaginary part. Let's look at two FIR filters. The first is 1 plus 1 over 2 z to the power minus 1. The second system is 1 over 2 plus z to the power minus 1. The first system represents a, because This is an FIR filter, so no pole will be there. All the poles will lie at the origin. And the important point is that a zero or a pole lying at the origin do not contribute anything to the transfer function. So but the poles and zeros will always be, the numbers will always be equal to each other. So here 1 0 is there, which lies at which lies at 0.5, rho equal to minus 0.5, and corresponding to that the pole will lie at the origin, since this is an FIR filter. No poles will be there anywhere inside the unit circle. And if you look at the other system, the second system, here the 0 is lying at -2. And how have you got this 0? If you take the reciprocal of this value, if you take the reciprocal of this value, which defines 0 here, so you get reciprocal of minus 0.5 is actually -2. If you take the reciprocal, the 0 will come outside the unit circle, but important point is that you are taking the reciprocal of the 0. So these two systems define this characteristic basically. Now H2Z is the reverse of the system H1Z. This is due to the reciprocal relationship between the zeros of H1Z and H2Z. Now if you we know that how to get the frequency response just by replacing Z equal to e to the power j omega. So for both the systems we get the frequency response, and we take the modulus of both the systems. The important point is that magnitude response for both the systems is same. This is important. When there is a relationship of this kind, that there exists a reciprocal relationship between the zeros of the two systems. That means one is just the reverse of the other. Once you take the reciprocal of the 0 for one system, and you will get the other system. In that case, the magnitude response will remain the same for both the systems. The magnitude characteristics for the two filters are identical because the roots of H1Z and H2Z are reciprocal. But as far as the phase part is concerned, phase will not be same. So we plot the phi 1 omega, the phase looks like this from minus pi to pi, right? Whereas in the case of phi 2 omega, the phase looks like this. So let's try to understand what is there in the note. If we reflect a 0, z equal to rho, that is inside the unit circle, into a 0, z equal to 1 over rho, as we did in our present system, what we were talking about. So that is inside the unit circle into a 0 outside the unit circle. The magnitude characteristic of the system is unaltered, but the phase response changes. And we observe that the phase characteristic phi 1 omega begins at 0 phase at frequency omega equal to 0. So at omega equal to 0, it begins from 0 for phi 1 omega and terminates at 0 at the frequency omega equal to pi. So it terminates at 0 at omega equal to pi or minus pi. So it starts from 0, it terminates at 0. Hence the net phase change from phi 1 pi to minus phi 1 0 is 0. So if you look at the phase response of this first system, you will see that the phase starts from 0, ends at omega equal to 0, and ends at 0 at omega equal to pi. So what is the net phase change? Net phase change is 0. This type of system is known as minimum phase filter. What is minimum phase filter? When the 0 is inside the unit circle. Now let's look at the second system. On the other hand, the phase characteristic for the filter with 0 outside the unit circle undergoes a net phase change of minus pi. Now if you look at this phase, it starts from 0, so you go to pi, there is a phase shift of from 0 to minus pi. So that's what is explained here. On the other hand, the phase characteristic of the filter with 0 outside the unit circle undergoes a net phase change of minus pi radians. As a consequence of these, different phase characteristics, we call the first filter a minimum phase system because the zero is inside the unit circle. The second system is called a maximum phase system because the zero is outside the unit circle, but there is a relationship between the zero for the first system and the zero for the second system. And there is a third possibility also. If a filter with m zeros has some of its zeros inside the unit circle and some outside the unit circle, then it is called a mixed phase system. Meaning by when all the zeros are inside the unit circle, that will be a minimum phase system. When the zeros are outside, all zeros are outside the unit circle, it will be a maximum phase system. And I have already explained the difference between the minimum phase and the maximum phase. And when out of m zeros, some zeros are inside the unit circle, and some zeros lie outside the unit circle, this will represent a mixed phase system. Okay, so I think the point is very clear about the minimum, maximum, and mixed phase system about the zeros. And of course, we know that the system will be stable system if the poles lie inside the unit circle. Once the pole is either at the unit circle, not z equal to 1, or outside the unit circle, the system is going to be unstable. A minimum phase property of the FIR filter carries over to IIR filter. So the same property also carries over to even IIR filter also. So if you consider an IIR filter, because you have the numerator and the denominator part both, that means the zeros and poles will always be there. Now this system is called a minimum phase if all its poles and zeros are inside the unit circle. All poles and poles, of course, for a stable system will lie inside the unit circle, and zeros are also inside the unit circle. That will be a minimum phase system for the IIR type. And if if the poles are inside the unit circle but zeros lie outside the unit circle, along the x-axis is the real part of z, along the y-axis is the imaginary part of z, because z is a complex number. If the zeros lie outside the unit circle, all poles lie inside the unit circle, that will be a maximum phase system. We looked this thing in the FIR filter case also. And if some zeros are outside the unit circle and some zeros are inside the unit circle, that will be a mixed phase kind of system. Okay. Now, this is one example I have taken to draw the phase pole zero plot. Consider a fourth order all zero filter. The this is the transfer function taken. This is the value of z actually. So four values of z are given. All right, because containing a double complex conjugate set of zeros located at z equal to uh, z 0.7 e to the power plus minus j pi by 4. So two zeros will be here, two zeros will be here. All poles lie inside the, all poles lie at the origin. That's why they will not contribute anything to the transfer function. The minimum phase, mixed phase, and maximum phase pole zero patterns have identical magnitude responses. Now, if you try to get the transfer function out of this, you can get the transfer function for all these systems, right? And you will, in that case, you will see that the magnitude response remains the same, and phase response, if you plot the phase response, you will get a different phase responses for all the three types of built systems. All right, so this is the magnitude part and this is the phase part. Okay, now let us talk about a very important filter, which is a second order resonant filter. We will now talk about the uh, complex conjugate pair of poles. This part is very important actually, because If the poles are real, in that case you will not be able to obtain a band pass filter. You will not be able to obtain the resonance taking place. The magnitude curve will not peak upwards. If it will not peak upwards, you will not be able to achieve a band pass filter. But if in a system, if you have a complex conjugate pair of poles, then resonance will occur and you will be able to design a band pass filter, because then the curve, the magnitude response curve will peak upwards. So once it peaks upwards, you can adjust the broadening of the peak, the sharpness of the peak to obtain a band pass filter. The condition for getting a band pass filter is that the system must have complex conjugate pair of poles. All right. Now let us consider two poles which are complex conjugate pair of poles, P1 and P2. It is R is the radius where the poles lie. R is the distance from the origin to the pole location, right? For both the cases, it is R e to the power j theta 0. One is theta 0. Basically, it is omega 0. All right. And this is also omega 0. And we get the values of, we can represent it as theta in the phasor in the polar coordinate system, but actually it is omega 0 only for the digital frequency. So we get, this is omega 0 only, r cos omega 0 plus j r sin omega 0, r cos, we can expand the e function like this. Now this is a two pole system. Now if it is a two pole system, the system will look like this. The structure of the system will look like this. It's an all pole, it's only two poles are there, but it's an all pole system. No zeros are there. So no zeros are there, no feed forward system, only feedback system will be there. So therefore there will be two poles, one delayed by 1 unit of time, the other delayed by second unit of time. And if this is the structure of the filter, then this will be the transfer function of the filter, 1 over 1 plus b1 z minus 1, b2 z to the power minus 2, and you multiply with z square up on the numerator part, and the denominator part you can modify the expression like this. All pole system has poles only without counting the zeros at the origin. So zeros will lie at the origin, that we have already discussed. Now this is the transfer function. If you factorize the denominator part, you will be able to factorize it like this: z minus p1, which is the first pole, z minus p2, which is the second pole. And these are the pole values: r e to the power j omega 0 and r e to the power minus j omega 0. Omega 0 is the particular frequency or particular digital frequency, because this is omega equal to 0. As you go on this side, the omega will vary, the digital frequency will vary. At this point the digital frequency is pi by 2, coming back at this point it is minus pi by 2, going like this it comes back here. So at omega 0, right, this pole locations are there. Omega 0, this pole lies, omega minus omega 0, so this pole lies, because these two poles are complex conjugate pair of poles. Now if these are the poles, you can put these values, you can multiply inside, you will be able to get this expression after doing the simplification. After putting the value of e to the power j omega 0, e plus e to the power minus j omega 0, you will be able to achieve this. Now this is after putting the values of the poles in the polar form and then expanding it into the rectangular coordinates. And if you compare this expression of the transfer function with the general expression of the transfer function defined in terms of b1 and b2, so you will be able to get the values of b1 and b2 from here. So b1 will be minus 2r cos omega 0, whereas b2 will be r square. From here you will be able to get cos omega 0 in terms of because what will be r here? R will be under root of b2. So if you substitute the values, you will be able to get cos omega 0, which is minus b1 over 2 under root of b2, and omega 0, which is the digital frequency, is 2 pi, because the relationship we know, digital frequency is equal to analog frequency multiplied by capital T. So analog frequency is given by 2 pi f0. So capital T is actually the sampling period. So it can be written as 1 over fs also. So that's the value of omega 0, which is the digital frequency, resonant frequency. At this frequency, the resonance will occur, and we will be able to get this value. Once the resonance will occur, you will be able to bend the magnitude curve upside. So it will be giving a band pass kind of response. Now let's look at the stability of the second order filter. So we are considering the two pole resonant filter, which looks like this. B1 and B2 are coefficients. Now if you look, because this will become a quadratic equation, it will have two roots. This system has two zeros at the origin and pole. Of course, the zeros are at the origin. Equivalent number of zeros will be there in the system, but they will lie at the origin, will not contribute anything to the transfer function. But the poles lie at P1, P2. These will be poles. You will be able to get the roots of the characteristic equation. You will get the quadratic equation you will get from here. You put it equal to 0, you will be able to get you will be able to get the roots of the equation. This will be minus b1 over b2 plus minus under root of b1 square minus 4b2 over 2. This is a standard quadratic equation formula for finding the roots. Now the filter is stable if the poles lie inside the unit circle. Or both these poles, if lie inside the unit circle, we know that the system will be stable only, because now we are looking at the stability in terms of b1 and b2 values, the coefficient values also. Now for stability, B2 has to be less than 1. Why? Because B2 is R square. So B2 has to be less than 1 because R is the radius of the distance from the pole from the origin to the pole location. So it has to be inside the unit circle. So therefore R has to be less than 1, right? So therefore it gives me B2 has to be less than 1. Now if B2 is equal to 1, that means R is also 1. In that case, the system becomes unstable, marginally unstable, and that will lead to an oscillator. Now we assume that the poles are complex. Now if the poles are complex, this part in the under root will be less than 0. So b1 square minus 4b2 should be less than 0. And we just manipulate this. We take 4b2 on the other side. b1 square is less than 4b2. We calculate b1 from here, which is plus minus 2 under root of b2. b2 has to be greater than 0. Now if it is greater than 0, then we get real roots. Of course, when this is inside the square root, whatever is there inside the square root, if it is greater than 0, greater than equal to 0, we get real roots. But if it is less than 0, we get complex roots with this relationship. Now the stability conditions define a region in the coefficient plane. Now we define a coefficient plane. Along the x-axis is b1, along the y-axis is b2, which is in the form of a triangle. Now let's look how we have plotted this curve. The system is stable only if and only if the point b1 comma b, any point in the graph, lie inside the stability triangle. Now if this is the shaded portion is the stability triangle. This is basically a parabola. b2 is equal to b1 square over 4. We know this value from here because this b2 is b1 square over 4. So let me have this. b2 is you get this value. So this is sorry, b1 is plus minus 2 b2 under root b2. So you will be able to get the value of, so from here you get the value of b2, right? And you can say that once you manipulate this, you have to square it. So in that case you will get b1 square, and 4 you will be able to get the value of b2, because that's a boundary we are taking. That's why we will take here the equal value, the equality value, and because that's the boundary beyond which the to explain the stability we will take the boundary value. So this defines the parabola. We get the parabola from b2 equal to b1 square over 4. Now let's look at the other boundaries. If the two poles are real and they must have a value between -1 and 1 only, they must lie here. They must lie on the real axis. If the poles are real, then the poles will lie on the real axis. If the poles are conjugate, then they will lie anywhere other at other position than the real part. Now, if the two poles are real, they must have a value between -1 and 1 for the system to be stable. Of course, the poles have to lie inside the unit circle. That means this is the pole values. The two pole values, they must lie between -1 and 1 if the poles are real. And you take 2 to this side, you take b1 to this side, and you adjust the equation, inequality equation like this. So -2 plus b1, one value will be with minus sign, the other value will be with positive sign. And ultimately you get two equations: b1 minus b2 minus 1 is less than 0, and b1 plus b2 plus 1 is greater than 0. You get two equations, and these two equations are put it like this. So this is b2 minus b2. If you look at here, b2 equal to minus b1 plus 1, b2 is equal to minus b1 minus 1, because b2 it's minus here. You get two equations. You get two equations from here, two boundary lines. We will take the equal values because we have to consider the boundaries. So b2 is equal to minus b1 minus 1, and the other equation is b2 is equal to b1 minus 1. This value is b2 equal to 1. So b2 has to be equal to 1 because it has to stay inside the radius has to stay inside. Now, what I'm trying to explain is that what should be the b2 and b1 values for so that the system remains stable. One curve we get is a parabola, which is this parabola, right? The other two equations are of the straight lines, other three equations rather. b2 equal to 1, b2 equal to minus b1 minus 1, b2 equal to b1. So this is one line, this is second line, this is third line. This forms a triangle. And what is parabola? It is b2 over, this is the parabola. Two things we need to note. One is the triangle. How did we get the triangle? And the other is the parabola. Now the region below the parabola, whatever is there below the parabola, b1 square is greater than 4b2 corresponds to real and distinct poles. So below this parabola, everything will be real poles, will define the real poles and distinct poles. Now the points on the parabola, right, result in real and equal poles. Distinct poles means two poles will be uh, uh, different, but if they lie on the parabola, so the same poles will be there, result in real and equal double poles. All right, the points above the parabola, if any point is above the parabola, in what are the values of what is the value of a point? It is in terms of b1 and b2. It is in terms of the coefficients of the transfer function. Now if any point lies above the parabola, that means that will lead to complex conjugate poles. Now we know that what coefficients are to select so that any point lies above the parabola, and we can get the resonance, and we can get a system like a band pass filter system. So this is how the second order resonant system looks like. in terms of if we analyze the behavior of the system and look for the stability of the system. Thank you very much. We will continue in the next lecture. Thank you.